93 million miles away, something just moved. A burst of energy tore itself off the surface of the sun with the force of 1 billion hydrogen bombs. And right now, it is crossing the gap between that star and this planet. Not in years, not in months, in hours. We gave it a name almost nobody outside a small circle of scientists will ever hear, an X4.2 class solar flare. But the name is not what matters. What matters is what it is dragging behind it, what it might still unleash, and what happens to a civilization built entirely on invisible electricity when the sun decides to remind us who is really in charge. This is the story of a storm that is not supposed to be dangerous, and why this time nobody is entirely sure that is true. To understand what is happening right now, you have to understand that the sun is not the calm, unchanging disk we grew up drawing in school. It is a churning ball of plasma wrapped in a magnetic field so complicated that even the scientists who study it for a living describe it, without irony, as a mess. That magnetic field does not stay still. It twists, it stretches, it gets tangled around itself like a garden hose left in the sun too long. And when it tangles badly enough, it snaps. That snap releases energy that has been building for days or weeks in an instant, a solar flare. The biggest ones can outshine the entire rest of the sun in X-rays for several minutes. Right now, one particular region of the sun's surface has become the most active piece of real estate in the solar system. Scientists have tagged it sunspot group 43166. Over the past couple of weeks, it has been throwing tantrums almost daily. An X1 flare, then an X1.8, an X2.8, an X1.6, and now the big one, an X4.2, rated Earth-directed, meaning it did not just happen to point at us. It happened while that patch of the sun's surface was aimed almost squarely at our planet. On the flare classification scale, letters matter as much as numbers. Key-class flares are minor, barely worth a headline. M-class flares are moderate, capable of some radio disruption. X-class flares are the big leagues, the ones capable of reaching Earth's upper atmosphere and briefly scrambling high-frequency radio communication on the sunlit side of the planet. Each whole letter represents roughly 10 times the energy of the one below it. An X-class flare is not just bigger than an M-class flare, it is an order of magnitude bigger. And this region has now produced 5 X-class flares in a matter of weeks, on top of dozens of strong M-class flares. That is not a quiet sun. That is a sun in one of its most turbulent moods in years. Here is where the story gets strange and where the real uncertainty begins. Normally, a solar flare of this size comes bundled with something far more physically dangerous. A coronal mass ejection, or CME, an enormous bubble of magnetized plasma, billions of tons of solar material hurled outward into space at speeds that can exceed 1 million miles an hour. If the flare is the flash of a gunshot, the CME is the bullet. The flash arrives in about 8 minutes, the time it takes light to cross from the sun to the Earth. The bullet takes anywhere from 1 to 4 days. But this X4.2 flare, like nearly every major flare this sunspot group has produced, did not launch a clearly Earth-directed CME. The plasma erupted and then largely stayed put. Scientists studying the region believe this is because the magnetic field above the sunspot is unusually strong. Strong enough to act like a lid, holding most of the ejected material down rather than letting it escape into space. Flare after flare, the pressure builds, and flare after flare, the lid mostly holds. Mostly. One eruption from the same active region, an enormous X8.1 flare among the strongest recorded this cycle, did manage to punch a coronal mass ejection free. It was not a picture-perfect direct hit. The bulk of the material is angled somewhat off from Earth's center, but models from US government space weather forecasters project it will begin brushing past Earth's magnetic field in the coming day, with the densest part of the plasma cloud arriving roughly a day after that. It is not moving especially fast as these things go. Somewhere in the neighborhood of 400 kilometers per second, modest by CME standards. Based on that speed and trajectory, the official forecast calls for a G1 or minor geomagnetic storm, the lowest rung on a 5-step scale that tops out at G5, the kind of planet-wide event associated with historic storms like the Carrington event of 1859, which set telegraph offices on fire and produced Aurora as far south as the Caribbean. This is not that. Nobody serious is suggesting it is. But here is the twist that space weather forecasters keep coming back to. The official forecast is a snapshot based on the data available right now. And the data available right now has a habit of being incomplete. Independent confirmation is starting to arrive from an unlikely source. A spacecraft called Solar Orbiter, currently stationed almost directly between the Sun and the Earth, but offset enough to the side that it can sample the incoming solar wind slightly before we do. In the last day, Solar Orbiter detected a sharp shock. Its onboard magnetometer jumped from a field strength of 17 nanotesla to 33 nanotesla in a short burst, a jump of roughly 15 nanotesla in a matter of moments. That is not a subtle reading. That is a spacecraft getting physically shoved by something moving fast. Something is coming. The only real questions are how hard it hits and what else might still be behind it. Because forecasters tracking this region point out something else. Repeated flaring, even without a clean, obvious coronal mass ejection, tends to churn up the solar wind in general. Think of it less like a single wave and more like a stretch of rough seas. More turbulence, more unpredictability, arriving in the same window as the confirmed CME. Several forecasters now believe the storm could run stronger than the official minor rating suggests, potentially reaching G2 or even G3, a strong geomagnetic storm capable of pushing the Aurora Borealis much farther from the poles than usual and capable of inducing measurable currents in long-distance power transmission lines. And there is a second, more unsettling possibility sitting quietly underneath all of this. Remember that magnetic lid, the one that has been holding most of this active region's eruptions in check. It is still there. Sunspot group 43166 has continued to grow physically larger even as its internal magnetic complexity has eased slightly. It remains squarely in what forecasters call Earth's strike zone, the central portion of the visible solar disk from which an eruption travels almost directly toward us. And it is expected to stay in the T-zone for roughly another day and a half before it begins rotating toward the edge of the Sun as seen from Earth. That matters because the fact that a truly major coronal mass ejection has not yet broken free from this region does not mean the plasma is not there. It means it is still trapped. And every additional X-class flare this region produces is, in effect, one more crack forming in that magnetic lid. If that containment fails cleanly while the active region is still facing Earth, something forecasters say remains entirely possible in the coming 12 to 24 hours, the result would not be a minor storm. It would be a genuinely major eruption aimed directly at us, arriving on top of a solar wind environment that is already stirred up, in a planet that has not yet finished absorbing the first wave. Nobody is forecasting a Carrington-level catastrophe. That kind of event remains, thankfully, rare. Something that has happened perhaps once or twice in recorded history. But the gap between minor storm, pretty lights, no real consequences, and strong storm, real infrastructure stress, is exactly the gap this event is sitting in right now. And that gap is precisely why space weather forecasters, usually a fairly understated group of scientists, are watching this one more closely than they have watched anything in months. So what does a geomagnetic storm actually do once it arrives? At the gentle end, a G1 or G2, the most noticeable effect is also the most beautiful one. Charged particles funnel down along Earth's magnetic field lines toward the poles, colliding with oxygen and nitrogen molecules in the upper atmosphere and making them glow. That glow is the aurora, normally confined to a narrow ring around the Arctic and Antarctic. But during a geomagnetic storm, that ring expands. A moderate storm can push the Aurora Borealis visibly south into the northern United States, southern Canada, and across much of Scandinavia and northern Europe. For skywatchers, this is the payoff. The reason photographers now travel deliberately to high-latitude locations during active solar periods, cameras ready, hoping the forecast holds. But the same particles that paint the sky are also, at larger scales, capable of quiet mischief on the ground. Geomagnetic storms induce small electrical currents in anything long and conductive. Power transmission lines, pipelines, railway signaling systems. During a strong storm, those induced currents can strain transformers, occasionally triggering protective shutdowns. Satellites can experience increased drag as the upper atmosphere heats and expands, subtly altering their orbits. GPS accuracy can degrade for hours at a time. High-frequency radio communication, still relied upon by some aviation and maritime operations, can experience blackouts on the sunlit side of the planet during the flare itself and disruption for longer during the geomagnetic storm that follows. None of this, at G1 through G3 levels, threatens the kind of society-wide blackout that occasionally makes headlines in worst-case scenario reporting. That level of consequence belongs to the rare extreme end of the scale. G5 events, the kind measured perhaps once or twice a decade at most, and the kind capable of the sort of widespread transformer damage that utility companies genuinely plan around. But not catastrophic is not the same as nothing. It is simply the space between a light show and a warning. Consider the layers of modern life quietly touched by even a moderate storm. Airlines flying polar routes between North America and Asia sometimes reroute flights slightly farther south during strong geomagnetic activity, both to avoid communication blackouts near the poles and to reduce radiation exposure for crew on long, high-latitude flights. Farmers using GPS-guided tractors for precision planting can see their equipment's positioning accuracy drift by feet rather than inches for a few hours. Oil and gas companies monitoring pipelines watch for induced currents that can accelerate corrosion over time. None of these are emergencies. All of them are the kind of small, distributed friction that adds up across an economy that has quietly wired itself to depend on a calm sun. This is also why utility companies and satellite operators do not treat space weather forecasts as background noise. Grid operators in regions with a history of geomagnetic sensitivity, such as Canada, the northern United States, and Scandinavia, can take preemptive steps when a strong storm is forecast, adjusting transformer loads or bringing additional reserve capacity online. Satellite operators can place spacecraft into safe modes, temporarily powering down non-essential systems to reduce the risk of damage from a sudden radiation spike. None of it makes headlines. All of it is why the difference between "we saw this coming" and "we did not" tends to matter far more than the storm's numerical rating alone. Earth has weathered far worse than this. And the historical record is the reason scientists are not panicking even while they are paying close attention. In September of 1859, a British astronomer named Richard Carrington watched an extraordinarily bright flash erupt from a sunspot he happened to be observing. Less than a day later, the resulting geomagnetic storm was so intense that telegraph operators across Europe and North America reported sparks jumping from their equipment, some machines catching fire, and others continuing to send messages after operators disconnected them from their batteries entirely, powered by the induced current in the wires themselves. Aurora were reported as far south as Cuba and Hawaii, bright enough that some observers reported being able to read a newspaper by their light at midnight. That event, now known as the Carrington event, remains the benchmark against which every subsequent solar storm is measured, and notably, the benchmark this current event falls dramatically short of. More recently, in March of 1989, a strong geomagnetic storm induced currents in Quebec's power grid, severe enough to trip protective relays and black out the entire province for roughly 9 hours, affecting millions of people in the middle of a Canadian winter. In 2003, a series of storms, nicknamed the Halloween storms, damaged satellites, disrupted airline navigation and communications, and caused a brief power outage in Sweden. These are the modern reference points forecasters use when trying to calibrate what a G2 or G3 storm might realistically mean for a technologically dependent society. The event unfolding now sits well below any of those thresholds, for now. What keeps forecasters watching closely is not what has already happened, but the fact that the source region has not finished producing. Perhaps the most important thing this event illustrates is not about this particular flare or this particular sunspot group. It is about timing. The sun operates on an 11-year cycle of rising and falling activity, and current evidence suggests we are near or past the peak of the current cycle, a period scientists call solar maximum. During solar maximum, sunspot groups like this one become more common, more complex, and more likely to produce exactly this kind of rapid-fire sequence of major flares. We are, in a very real sense, living through the loud part of the sun's cycle. That has consequences that reach well beyond aurora photography. Modern civilization runs on systems that did not exist the last time the sun was this active. GPS-guided agriculture and aviation, satellite-based financial transaction timing, a power grid that is more interconnected, more automated, and in places more aging than ever before. Space weather forecasters working out of agencies with names most people have never heard monitor this activity around the clock, precisely because the consequences of getting caught unprepared have grown alongside our dependence on the technology at risk. This is not a reason for alarm. It is a reason for the same kind of quiet, competent monitoring that meteorologists apply to hurricanes. Tracking a system, refining a forecast as new data arrives, and being honest when that forecast still has real uncertainty attached to it. As of right now, the official forecast still reads G1 minor. The confirmed coronal mass ejection is still projected to arrive within the coming day, with the densest plasma following roughly a day after that. Skywatchers across Northern Europe and North America are being told to expect a good, possibly a very good night for aurora. But underneath that modest official number sits a more complicated picture. An active region that keeps producing major flares without fully releasing its pent-up energy. Independent spacecraft data showing a real shock already in transit. And a strike zone that remains pointed almost directly at us for at least another day. Somewhere above us tonight, that story is still being written. Not by us, but by a star 93 million miles away. It has just reminded an entire planet how small the gap really is between a quiet sky and a storm. We will be watching. That story, still unfolding above our heads, is being written in layers of data that arrive from different instruments at different times. The first layer is the flare itself, the burst of X-rays and extreme ultraviolet radiation that reaches Earth in just over 8 minutes. That part of the event is already done. High-frequency radio operators on the sunlit side of the planet may have noticed brief blackouts or degraded signals during the peak of the X4.2 flare. Aviation crews on polar routes may have adjusted their communications plans. But that initial pulse, dramatic as it is only the opening act. The second layer is the coronal mass ejection that did escape, the one associated with the earlier X8.1 flare from the same active region. That cloud of magnetized plasma is now moving through the space between the Sun and Earth, and its arrival is what will determine whether this event remains a minor geomagnetic disturbance or escalates into something more significant. Forecast models based on observations from satellites such as SOTO and STERO give an estimated arrival window, but those models are only as good as the data fed into them. If the CME is faster than expected, if its magnetic field is oriented in a particularly impactful way, or if it interacts with other structures in the solar wind along the way, the actual storm could differ from the initial forecast. The third layer is the background solar wind environment, which has been churned up by weeks of repeated flaring from sunspot group 43166. Even without a clear, Earth-directed CME for every flare, the cumulative effect of all that activity is a more turbulent solar wind. That turbulence can amplify the impact of an incoming CME. Much like a wave hitting a boat in rough seas has a different effect than the same wave in calm water. This is one reason why some forecasters are cautious about relying solely on the official G1 rating. The environment into which the CME is arriving is not quiet. It is already disturbed. The fourth layer is the possibility of another eruption. Sunspot group 43166 remains in Earth's strike zone, and it has shown no sign of settling down. Every additional X-class flare it produces increases the chance that the magnetic lid holding back the bulk of the plasma will finally give way. If that happens while the region is still facing Earth, the resulting CME could be faster, denser, and more directly aimed than the one already in transit. That scenario is not the most likely outcome, but it is plausible enough that forecasters are keeping a close eye on the region for the next day or two. All of these layers combine to create a situation that is more complex than a single headline number can capture. A G1 forecast does not mean nothing will happen. It means that, based on the best available data, the most likely outcome is a minor geomagnetic storm. But most likely is not certain, and the uncertainty is concentrated in exactly the places that matter most for infrastructure. The speed and density of the incoming plasma, the orientation of its magnetic field, and the state of the solar wind it is moving through. That uncertainty is why agencies such as NOAA's Space Weather Prediction Centre and the UK's Met Office Space Weather Centre issue updates regularly, sometimes hourly, as new data becomes available. They are not just watching the clock, waiting for the CME to arrive. They are monitoring real-time measurements from satellites positioned upstream of Earth, such as ACE and DSCOVR, which sit at the L1 Lagrange point about 1.5 million kilometers sunward of our planet. These spacecraft act as early warning buoys, measuring the solar wind's speed, density, temperature, and magnetic field before it reaches Earth. The most critical measurement is the BZ component, the north-south orientation of the interplanetary magnetic field. If BZ is strongly southward when the CME arrives, it can connect efficiently with Earth's northward-pointing magnetic field, opening the door for energy to pour into the magnetosphere. That is when a modest CME can produce a stronger-than-expected storm. If BZ is northward, the coupling is weaker, and the storm may fizzle out despite a fast or dense plasma cloud. The problem is that BZ cannot be measured until the CME is almost at Earth, typically 30 to 60 minutes before impact. That short warning time is why forecasters emphasize probabilities rather than certainties. For the general public, the most visible sign of all this activity will be the aurora. If the storm reaches G2 or G3 levels, the auroral oval could expand far enough south to be visible from parts of the northern United States, including states like Michigan, Minnesota, and Maine, as well as southern Canada, Scotland, and northern Europe. Under dark skies, away from city lights, observers might see a green or reddish glow low on the northern horizon, or, if the storm is strong enough, curtains of light dancing overhead. Photographers and aurora chasers are already planning their outings, checking cloud forecasts and geomagnetic indices, hoping the conditions align. But for the operators of critical infrastructure, the aurora is a side effect, not the main concern. Grid managers are watching geomagnetic indices and transformer temperatures, ready to adjust loads or take other protective measures if needed. Satellite operators are monitoring radiation levels and atmospheric drag, prepared to put spacecraft into safe mode if conditions deteriorate. Aviation authorities are tracking high-frequency radio conditions and radiation levels at high latitudes, ready to reroute flights if necessary. None of these actions are dramatic, but they are the practical expression of a society that has learned to live with a variable sun. The fact that all of this is happening during solar maximum adds another layer of context. We are not in a quiet period where a single active region stands out as an anomaly. We are in a phase of the cycle where multiple active regions can appear, evolve, and produce flares in rapid succession. That means the potential for compound events, where multiple CMEs interact with each other or with the background solar wind, is higher than it would be during solar minimum. It also means that forecasters are dealing with a more dynamic and less predictable environment. That does not make this event uniquely dangerous. It makes it representative of the kind of space weather we can expect more of as the sun moves through the peak of its cycle. The question is not whether there will be more flares and CMEs. There will. The question is how well prepared we are to handle them, and whether the systems we depend on can withstand the cumulative stress of repeated moderate storms, not to mention the low probability, high-impact extreme event that remains a possibility before the cycle ends. Preparedness, in the context of space weather, is not about building a bunker or stockpiling supplies. It is about designing systems that can tolerate a certain level of disturbance, monitoring conditions in real time, and having procedures in place to respond when those conditions exceed normal thresholds. For the power grid, that means transformers that can handle induced currents without overheating, protection systems that can isolate problems before they cascade, and operators who understand the space weather forecasts and know what actions to take when a storm is coming. For satellites, preparedness means radiation-hardened components, redundant systems, and the ability to enter safe mode when the space environment becomes hostile. It also means tracking orbital decay due to increased atmospheric drag and adjusting station-keeping maneuvers accordingly. For aviation, it means alternative communication routes, radiation monitoring for crew on high-latitude flights, and the flexibility to reroute when necessary. For GPS-dependent industries, it means having backup systems or correction services that can maintain accuracy even when the ionosphere is disturbed. None of these measures eliminate risk entirely, but they reduce the likelihood that a moderate geomagnetic storm will cause significant disruption, and they buy time for the more extreme scenarios, the ones that keep planners awake at night. The Carrington event of 1859 remains the gold standard for worst-case planning, not because it is likely to be repeated exactly, but because it shows what the sun is capable of when conditions align in just the right way. A storm of that magnitude today, hitting a world far more dependent on electricity and electronics than the telegraph-era planet, would have consequences that are difficult to overstate. That is why governments and international organizations have been working to improve space weather forecasting and response over the past couple of decades. NOAA's Space Weather Prediction Center in the United States, the Met Office in the UK, the European Space Agency's Space Weather Service Network, and similar agencies around the world are part of a global effort to monitor the sun, model the solar wind, and communicate risks to stakeholders. They issue daily forecasts, alerts, and warnings, much like their terrestrial weather counterparts, but focused on the space environment. The tools they use are a mix of ground-based and space-based instruments. Ground-based observatories monitor the sun in visible light, tracking sunspots and active regions. Radio telescopes observe solar flares and coronal mass ejections. Magnetometers around the world measure changes in Earth's magnetic field, providing real-time data on geomagnetic activity. In space, satellites such as SOTO, SDO, STERO, ACE, DSCOVR, and now Solar Orbiter provide a multi-point view of the sun and the solar wind, allowing forecasters to see eruptions as they happen and track them as they move toward Earth. Solar Orbiter, in particular, is adding a new dimension to this effort. By orbiting the sun at a closer distance than Earth and at an inclination that allows it to see the sun's poles, it provides data that was not available during previous solar cycles. Its measurements of the solar wind, magnetic fields, and energetic particles help scientists understand how eruptions evolve as they travel through space and how they interact with the background solar wind. The sharp shock it detected recently, with the magnetometer jumping from 17 to 33 nanotesla, is an example of the kind of real-time data that can refine forecasts and reduce uncertainty. But even with all these tools, forecasting space weather remains an imperfect science. The sun is a complex, nonlinear system, and small changes in initial conditions can lead to large differences in outcomes. A CME that looks like it will miss Earth can be deflected by another eruption and hit us instead. A modest flare can be followed by a much larger one if the underlying magnetic field continues to evolve in unexpected ways. That is why forecasters emphasize probabilities and scenarios rather than single-point predictions. They are not trying to say exactly what will happen. They are trying to outline the range of possibilities and their likelihoods. For the public, that can be frustrating. People want to know whether they will see the aurora, whether their power will go out, whether their GPS will stop working. The honest answer is that, for a G1 or G2 storm, the most likely outcome is a beautiful light show in the north and no major disruptions on the ground. But most likely is not guaranteed, and the small chance of something stronger is why forecasters and infrastructure operators are paying attention. The communication challenge is real. Space weather is not as intuitive as terrestrial weather. Most people understand what a hurricane or a tornado looks like and what it can do. Fewer people have a clear mental model of what a geomagnetic storm is and how it affects technology. That gap in understanding can lead to either complacency or unnecessary alarm. The goal of agencies and scientists is to strike a balance, to inform without frightening, to prepare without panicking, and to be transparent about what is known and what is not. In that spirit, the current situation is being described as worth watching rather than cause for concern. The active region is still capable of producing more flares and possibly another CME. The incoming plasma cloud could interact with the solar wind in ways that strengthen the storm. The magnetic field orientation at arrival could turn out to be more impactful than expected. All of these are reasons to monitor the situation closely. But none of them, at this stage, point to a high probability of a severe event. For skywatchers, that means keeping an eye on the forecasts and being ready to head out if the conditions align. For everyone else, it means carrying on with normal life, secure in the knowledge that the systems we depend on are designed to handle this kind of activity, and that there are people watching the sun around the clock to make sure we are not caught off guard. The sun has reminded us, once again, that it is not a passive backdrop to our lives. It is an active participant, capable of sending storms our way with little warning. But we are not helpless. We have learned to read the signs, to prepare for the weather in space, and to find beauty in the storms that result. That beauty, the aurora, is often the most tangible connection people feel to a space weather event. It transforms an abstract phenomenon, measured in nanoteslas and kilometers per second, into something visible, emotional, and shared. Social media fills with images from northern latitudes, people gathering in fields and on rooftops, cameras pointed skyward, hoping to capture the dance of green and red light. For a few hours, the sun's distant violence becomes a communal spectacle, a reminder that we live in the atmosphere of a star, not just on a planet. But the aurora is only the visible tip of a much larger process. Beneath the glowing curtains, Earth's magnetosphere is being compressed and reshaped by the incoming solar wind. Electric currents flow through the upper atmosphere, heating it and causing it to expand. That expansion increases drag on satellites, particularly those in low Earth orbit, which can affect their trajectories and lifetimes. The same currents that create the aurora also flow through the ground, seeking out long conductors like power lines and pipelines, where they can induce voltages that stress equipment. For grid operators, the challenge is to distinguish between normal fluctuations and those caused by geomagnetic activity. Modern power systems are equipped with sensors and protection devices that can detect abnormal currents and voltages, but the response must be calibrated carefully. Overreacting can lead to unnecessary shutdowns and economic losses. Underreacting can allow damage to accumulate, potentially leading to equipment failure or, in extreme cases, cascading blackouts. The experience of Quebec in 1989 is a constant reference point, a reminder that the risk is real, even if the probability of a similar event is low. Satellite operators face a different set of challenges. The increased radiation during a geomagnetic storm can cause single-event upsets, where a charged particle flips a bit in a computer's memory, potentially leading to malfunctions. To mitigate this, satellites are designed with radiation-hardened components and error-correcting software. But when the radiation environment becomes particularly harsh, operators may choose to put spacecraft into safe mode, shutting down non-essential systems until conditions improve. This is a precautionary measure, not a sign of imminent failure, but it can affect services that depend on those satellites, such as communications, navigation, and Earth observation. For aviation, the primary concerns are communication and radiation. High-frequency radio, used for long-distance communication over oceans and polar regions, can be disrupted by ionospheric disturbances during a storm. Pilots and air traffic controllers have alternative communication methods, but the disruption can still cause delays and require